Hi everyone. I'm seeing that my audio levels and everything is good, but as usual, if people can just let me know in the chat there if you can hear me, and that'll just reassure me that all the indicators that I have at my end are actually correct and that things are working. So let me just start introducing what I'm going to do today. I'm going to do some problems we're on 2D kinematics, which is thanks, Jeff. I'm going to do problems on 2D kinematics, which is the videos that you should have watched this week, and uh, basically that's it. And so the 2D kinematic videos that you should have watched were one on constant acceleration. So this is like falling, but the falling that we did in 1D was just falling straight down, or I might have thrown something up, it went up and then comes straight down along a line. But now we can throw things at an angle and it'll make that characteristic parabolic path. So that's 2D kinematics. And the other 2D kinematics that we studied, special case, was uniform circular motion. That's when an object is moving on a circle, and circle means constant radius, but also a constant velocity, okay? Later in the course, we'll do what's known as rotational motion, and we'll generalize that, where you can have something on a circle, but maybe it starts slow and then it speeds up, or conversely, it could be going fast and then slows down. That's not uniform circular motion because the velocity itself is changing. Okay, so let me show you the problems that we're going to do. One of them is a projectile problem. That's number one, and I've got five parts in there, so we'll go through those in details. And in particular, I'm going to show you how to draw the diagram systematically, the way I did in 1D. Okay, I have problems 2 and 3 there. They're variations on the first problem. I'm not going to do them. I'm going to expect you to do them on your own just for practice. This is in addition to the assignment, which you'll be doing next week, which will also have 2D kinematic problems on it. But they're just variations on the first problem. So one of the things you should do after after the live stream is you should just repeat the problem I did, even with the same numbers. You don't have to change the numbers. Repeat the problem I did, and then do the variations on it and see how they compare to one another. Okay, and then the last problem is really fast. It's on uniform circular motion. I'm just on a bicycle going around a corner. Most of these uniform circular motion problems are fairly straightforward. There's not much that you can do with them. So we'll do that one last. Okay, so let's begin. So the first problem I have is I'm standing at ground level and I throw a ball with an initial velocity of 25 meters per second. That's not too fast. That's easy to do, 25 meters per second, at 60 degrees above the horizon. And what that 60 degrees above the horizon means, I'll show you that in a minute. And it lands at the top of a hill, which is 20 meters high. Okay, and then I ask a series of questions. How long until it reaches maximum height? And what is maximum height? That's part B. Then part C, how long before it lands on the top of the hill? Okay, and how far did it travel horizontally before it lands on the before landing on the top of the hill? And finally, what's the velocity when it lands at the top of the hill? Actually, what's the velocity just before it lands on the top of the hill? Because I don't want the ball to interact with the hill. Then you can't use the equations that I gave you. Okay, so let's begin. Just reading the problem, what you should do first is draw a picture of physically what you would see. Okay, so I'm going to switch my other whiteboard here, and I'll do this part in black. And so here's ground level like this, and here's the hill, and there's the top of the hill like that. Okay, and it's what I say, 20 meters high, but I don't have to draw that right now. That'll come in when I draw the coordinate system. And then here I am at the ground level. Okay, I'm not even going to try to draw a picture, a stick figure of me or anything like that. I throw the ball and I throw it up at about 60 degrees, which is left roughly like that. And it goes up, 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 and comes down like that. Okay, so that black line there is just the trajectory. Okay, and that's it for the what you would physically see. Okay, basically you just see the ground and the hill, and then you see the trajectory of the ball as it goes up and it comes down onto the ground. The next thing that you need to do is draw in a coordinate system. And when you say coordinate system, what you mean is basically something to measure distances and also measure time. Both of them go hand in hand, although it's not possible to really draw time because this is a picture, not a movie. But you know, at least you should say where in that where along that trajectory the ball is at t equals 0. Okay, and I'll do this in blue. All right, and since this is 2D, you have to have two axes. You're going to have the x-axis, which we will always put horizontally like this. There's the x-axis. like that. So positive x like that. And you need a perpendicular to that, you need the y-axis, which is like that. Okay. And let me just fix that spot right there. Okay, and then the origin, so that's plus y, like that. And the origin is going to be where the two axes cross. That's 0. I'll just put a 0 there. It's really two zeros because it's 0 along x and 0 along y. But I'll put a single 0 in there. And you say, well, where along this trajectory is going to be, are you going to choose t equals 0? And you could choose it anywhere you like, but I think it's pretty obvious that we'll choose that point right there as t equals 0. In other words, if I had a stopwatch and I have to start the stopwatch going, at what point would you, click on the stopwatch? And I would do it when I release the ball. Okay. A couple of comments here. The way the equations, which I'll give you in a minute, the way I set up those equations, you have to have the x-axis horizontally and you have to have the y-axis vertically. You actually could choose them at any angle you want. And after the test, when we do Newton's laws, you'll see that I will actually change the x and y orientation. But for this particular problem, for these types of problems, you want the x-axis horizontally, the y-axis vertically. Otherwise, the equations that I'm going to give you will not work. Okay, and well, that's it. Okay, so the reason you set this all up is because you need to now read off the values of the initial position, the final position, the initial velocity, the final velocity, acceleration, and well, time is not a scale, is not a vector, but it's a scalar. But you still need times at the various points. Okay, and when I say initial position now, it's not a single number because let me do this in red. So I'm just going to pick a random point here. Let me just pick that point right there. Okay, I'll erase it in a minute. But if I were to ask you where is that point, which is a position, when you say position, you're answering the question where is it. If I say where is that, well, you can't just give me a single number. If you just give me the x, how far along the horizontally it is, then you're telling me, yeah, you're telling me that you would, if you projected a shadow down here, you would tell me like where it would measure there, but you wouldn't be telling me how high it is. Okay. Conversely, if you tell me, the y value, well, great, I kind of know how high it is, but I don't know where it is horizontally. So you need both numbers. Okay. So in 2D, you need both x and y coordinates. And so we're going to start off with the initial position, and it's two numbers. It's x naught, which is the x component of the initial position, and y naught, right? That pair right there, that is initial position. And you'll see this on the assignment that I give you over the, well, for next week, and also on the test. I kind of walk you through these problems, and so I say, I set this up for you, and I say, what is the initial position? And you'll see that, because it's multiple choice, you'll see my answers, and my answers will be like x naught is equal to something, y naught is equal to something. Okay, so all the possible choices will have two numbers associated with them because the initial position is two numbers. Okay, so where is this thing initially? Well, it's that initial, that little knot there means that t equals 0. Well, it's at the origin. That's where I release it. And so that's pretty easy. That's x naught is 0 meters and y naught is 0 meters. Okay, so let me look over at the chat here. If there's any questions. Okay, and actually there's very little lag today, so that's good. All right, and there you go. There's the initial. Now the next one that I like to do is the final position, and the word final is not the best name for this. It means where it is after a time t, the point of interest. And there's really 2 points of interest. For part A and B, I say maximum height, and that's here. Okay. And for parts C to the N, I say when it lands on the top of the hill. So you say, well, which one's the final? Well, if you're interested at maximum height, then that maximum height, we call that the final. And that's kind of a funny name for it because it doesn't stop there, okay? But, that is the point of interest after a time t. It's at the maximum height. I might have called it something different. I'm going to call it final because every textbook in physics calls it final, and there's no reason for me to change that language because then if you, were to compare my course with another course, you'd say, well, why are they calling it final in that course and you didn't? Okay, so that's the final position when it gets to maximum height, okay? And so over here, again, we can get two numbers. This we'll call x and y, okay? And there's your final position. And if you think about this, you don't know either of them. You don't know x because you don't know how far it traveled horizontally by the time it got to maximum. And you don't know the maximum height. In fact, that is part B. Okay, and so you don't know either of those. All right, that's fine. You just put question marks there. And there you go. Now the next one is the initial velocity. And the initial velocity is the one that's most interesting because we did all that work on um, uh, last week of converting vectors, converting from Cartesian to polar, polar to Cartesian, and so on. And you might wonder, well, why did you do that? And the reason is that all of these equations that we're going to use are Cartesian. And so if I give you polar information, you're going to have to convert it to Cartesian. And if you listen to how I gave you the information about the initial velocity, I say that I toss it with a velocity of 25 meters per second at 60 degrees above the horizon. And so what I'm effectively giving you is, let me see if I can draw this in a different color. Let me try green here. I'm telling you that the initial velocity is up this way, that green arrow there like that, or that green line there like that, okay? So there's the initial velocity, and I'm telling you that that initial velocity is 25 meters per second, okay? And at an angle of, so the horizon, like if you were standing at ground level and you looked out towards the horizon, I know there's a hill there, but if you look out towards the horizon where at a far distance where the Earth meets the sky, and that would be along the x-axis, and the angle I tell you is 60 degrees, okay, like that. And if you take a look at these two numbers, the 25 and the 60 degrees, they are not x and y components. What are they? They're the magnitude and the angle. Now, magnitude in the vector lecture, that was r, and the angle is theta, okay? So effectively, I'm giving you r and theta for the initial velocity, and what you need is, for the equations, I'll show you them in a second, is you're going to need v naught x and v naught y, like that, okay? And the formulas for those are, so I gave them to you in terms of r and theta, thinking about position, but if you were to think about this now in terms of a velocity, it's the magnitude of the velocity, which is just v naught, that's your 25 cosine theta, and vy would be the same, v naught sine theta. I don't have enough room to actually work that out on the diagram, so I'll do that on my text editor in a second. But there you go. Those two together are going to be your x and y components of the initial velocity. Okay, and the final velocity, well, let me do that also on the text editor. So I'll switch over because I'm running out of room on this diagram, and it's going to get pretty messy by the time I'm done. So there we are. Okay, so at this point, let me just, so we're working on question A, put some space in there. Let me just cut and paste the answer. I won't go too quickly. I just found that I tend to make less typos if I just cut and paste. There we go. Okay, let me see. Can you see that? Yeah. Okay. So I'm just transposing the numbers that we found on the diagram to this the text editor here, and this was the initial position right there that you see in highlight. It's the x naught and y naught. Okay, the final position, that's when it reached maximum height. That's your x and y, like that. Okay, and I say solve for this. I should have said solve for this in part B. Okay, all right. And we gotten this far here. So that was your initial velocity x component and initial velocity y component. Okay, and so if you plug in v naught, that's your magnitude, that's 25. The angle was theta, was 60 degrees, and cosine of 60 is one of those angles that you should know the value of. Cosine of 60 degrees is a half, okay? Sine of 30 degrees is a half, and cosine of 60 degrees is a half. They're good numbers to remember because then you can, just as a check on when you do it with your calculator. So 25 times a half is 12.5 meters per second, and the initial y velocity y component of the initial velocity. 25 sine theta turns out to be 21.7 meters per second. Okay. Now, I want to show you. So I'm going to switch back in a second. I want to show you what an interpretation of those two values are. Okay. And so if you go back to the diagram, you're wondering, well, how do I interpret the v naught x and the v naught y? Well, there's that green vector there. Let me I guess I can do it in red. Let me just kind of do a little dash line there. This little red piece here, that red arrow there, that's your v naught x. And then if I project the vector there, this red arrow going up like that, there's your v naught y. Okay. And you say, but it's a velocity, which means it's moving over time. It's the object's moving over time. That's right. So now let me actually do it right here. So there's the ball. If you looked at the shadow of the ball, so suppose the sun is directly overhead, and you look at that shadow of the ball actually moves to the right underneath the ball itself, and the shadow of the ball, at least initially, moves at 12.5 meters per second. So that yeah, the ball is moving up and down, okay, along the parabolic path, but its projection, that is its shadow along the x-axis, you could even extend it all the way down here. The shadow along the x-axis moves at 12.5 meters per second. Okay, and then along the y-axis here, you could do the same thing, although the sun doesn't shine vertically. Sorry, I guess it does. You don't get a shadow along the y-axis, but imagine that you had a light to the right of the diagram there, and it was just projecting a shadow onto the y-axis. Then, if you watch the shadow, the velocity of the shadow, it would at least initially be 21.7 meters per second. Okay, let me erase that and go back. So I did that just to give you an interpretation of what that 12.5 and 21.7 mean. Okay, and since they're projections, those numbers always have to be less than 25. Okay, and they are. Like 21.7 is a little bit less, but it still is less. Okay, and then that was the initial velocity. We can also do the final velocity. Usually you don't have enough information to get all of the final velocity, but for the Vx, you do know it. Vx is equal to v naught x, and the reason for that is that there's no acceleration in the x direction. That was actually the reason why I put the y-axis vertically and the x-axis horizontally. When you drop something, it accelerates down. So if your x-axis is horizontal, y-axis vertically, the acceleration is purely along y. There's no component of the acceleration along x. It'd be a very strange world if you drop something and it falls not only down but a little bit to the right, or it falls down and a little bit to the left. If there was a little bit of left or right acceleration, then you'd have an ax, okay, an x component to the acceleration, but there isn't. It falls straight down, and so there's no x component to the acceleration. If there's no x component to the acceleration, it means the velocity in the x direction doesn't change. The x component of the velocity doesn't change. And so whatever the initial velocity is, v naught x, that's what your velocity is at any later time. And so that shadow that moves along the x-axis continues at 12.5 meters per second, okay? The next one is a little harder to see. I said here Vy is equal to 0, and you might wonder why. And the reason is that when something goes up, okay, and it reaches its maximum height, so before it reaches the maximum height, it was moving up, so it had a little bit of a velocity upwards, an upwards velocity, okay? And then it stops, and then after it reached maximum height, it has a little bit of a downwards velocity. So it switches from an upwards velocity to a downwards velocity at maximum height. Exactly at maximum height, there is no velocity up or down. Okay, there can be a velocity to the right or the left, so Vx is not 0, but there can be no component of the velocity up, because if there were, it would continue to go up, and that wouldn't be maximum height. At maximum height, the y component of the velocity is 0. So that's why Vy is equal to 0 there. In fact, you can almost say that this is the defining feature. Defines max height. Okay? So as soon as you hear max height, think Vy is equal to 0. I know we had that in 1D, but in 1D it was pretty simple. There was only one velocity, and that, obviously that was the 0 velocity at the maximum height. But here we have two components of the velocity, and it's the y component that's 0 that defines maximum height. Okay, so then there's your acceleration, and it's downwards. So minus and 9.8, but we're rounding off to 10 in the course, and we'll round off for 10 in the assignments and on the test too. Okay, and then the time to reach maximum height unknown. In fact, that's what I'm asking you to solve for in this one. Okay, how long before it reaches maximum height? Okay, so 3 steps in drawing the diagram. First, draw the picture, put the XY axis on it in time, and then read off of the numbers off of that diagram. Read the values of initial position, final position, initial velocity, final velocity, and so on. And if any of the information is in polar, converted to Cartesian. Now you're ready to substitute into the equations. And, like the test is multiple choice. So you think, well, maybe I can be a little bit sloppy, but trust me, this is worth it. And for this problem, like, if I will have a problem with projectile motion. It won't just be one question. It'll be several questions referring to the same physical situation. So it is worth the time to draw the diagram properly, carefully, and make sure that you follow these steps. Then the chances of you going wrong are very slim. Okay. Now that we have this, we can plug into these equations here. Okay. And actually, before I go any further, I should look at the chat here and see if anyone has any questions. And doesn't seem like anyone is having any questions. I mean, the whole point of doing this interactively is for you guys to ask questions and for me to be a little bit less formal than the pre-recorded lectures. But okay, if you have no questions, let me go on. Okay, so what you have here are 4 equations, and only the last equation, number 4, is about x information. Okay, and the reason that the x equation is so simple is because ax is equal to 0. Okay, and so there's no acceleration in x. It just turns out to be this one equation here in terms of how far you move horizontally in terms of your initial velocity. Okay, but for the y part, the vertical motion, it's just like 1D motion, because you still have an acceleration down, and so you get the same equations that you had in 1D, but now translated into y information. Okay, so instead of x in 1D, you have y. So you have the equation y as a function of time. Okay, and that tells you how high it is at different times, and of course that requires you to know ay and v naught y, and of course y naught. Okay, then there's the second one, which is the Vy as a function of time. Okay, and so there's Vy at a later time, given an initial velocity, y component of the velocity v naught y, and an acceleration ay. Okay, and then the third one just eliminates time between those other two. So if you have a problem where there is no time, where I don't give you time information, or I don't ask for time information, then equation 3 might be the equation that'll help you. Okay, well, in this problem I asked for time. And so you say to yourself, well, which one can I use? And you don't know why, the maximum height. In fact, that's what you want to calculate. And you don't know the time to get the maximum height. So that's what these numbers are for. Looking at these numbers, I don't know why, and I don't know time. So I can't use the first one. Okay. And you want time. So can you use this one, number 2? And the answer is yes, you can use number 2. Number 3 you can't use because we're looking for time and it doesn't have time. And number 4 you can't use because we're talking about maximum height, and that's vertical motion, not horizontal motion. Okay, so you got to use number 2, and it really is quite simple. So I'm just going to cut and paste and give you that answer. If I'm going too fast with the cutting and pasting, I assume you're taking notes as I do this. I know you can watch these later, but it's good to take notes as I'm doing them. If I'm going too fast for you, just say slow down, and I'll be happy to do that. But so you can see how I reasoned it out, looking at the numbers that I had there, the values that I had. I said, well, I want to find time, and I know these values, and so number 2 is the one that you want. Okay, so use number 2 to get the time, and that's Vy is equal to Ayt plus V naught y, and Vy, maximum height, 0, Ay negative 10, t is unknown, and V naught y is 21.7. Rearranging, you get 2.17 seconds until you reach maximum height. Okay, so yeah, in some ways, just plugging into the equation is the easier part of this. I think, having taught this many years, most mistakes are made in getting the correct values. Okay, most mistakes are made, in getting these values here. And so I'm trying to show you a foolproof way of doing that, going by drawing the diagram carefully. Okay, so the next one is, what is the maximum height achieved? Okay, in other words, we want to solve for y. Now, if you go back to these and you say, well, I want to solve for y, there's only two equations with y in it, number 1 or number 3. And at this point, you know time, so you could use number 1 or you could use number 3. And I even forget which one I used. I think I used number 3. You could use either one. Yeah, I use number 3, but there's really, I don't know if there's even a preference for which one is easier to use, but both of them will give you the answer. This happens a lot. Usually the first question that you answer, there's only one equation that'll solve it. But then once that happens, they unravel because these equations are all interrelated, okay? And so what we have here is use either 1 or 3. Let's use number 3. So that's the one that has vy squared is equal to v naught y squared plus 2ay y minus y naught. Okay, and so vy is 0. Okay, v naught y we found above was 21.7 squared. 2 times negative 10. Y minus y naught is 0. Okay, and I got 23.5. Maybe I went a little bit too quick there. I kind of like just reduced it, so that's 0. And where's my calculator? What is it? 21.7 squared. Okay, so that's equal to this value here. Let's round it off. Minus 20y, like that. Okay, and so now all you do is just solve for y in that, and that's pretty easy. And you get 23.5 meters. Okay, and so that's the maximum height. It better be higher than 20 meters, otherwise it wouldn't get to the top of the hill. Okay, so if that happens, then I made a mistake. So I'll endeavor not to make any mistakes. Okay, so that answers the first two questions. All right, let me take a look in the chat here. All right, no questions, so I assume everyone is good with this. Either everyone is good or people are falling asleep at the keyboard. All right, so how long before it lands on the top of the hill? Now, you got to watch these questions, okay? You have to kind of repeat, like parts A and B, they went together. You didn't have to like rethink the whole problem for part B. Part A and B were both about maximum height. Okay, so the final position was maximum height, but you got to watch it because I did something here. I said how long before it hits lands on the top of the hill, and as soon as you say top of the hill, your final position is changed, and so you have to rethink the numbers. But you probably don't have to redraw the diagram, okay? But you have to rethink the numbers that you're going to get out of the diagram because now your final position is different. Let's go back to the diagram and see what I mean by that, okay? So over here in the diagram, let me do this in purple. All right. Now, like before, see that red dot at the top there? That was your final, but now the final is down here. Okay. Now, the whole point of this diagram is to read off the numbers. And so if you move your final around or you move your initial around, then your numbers are going to be wrong and you have to rethink them. Okay, so I don't have to redraw the diagram, but I got to rethink the numbers. And I go in this order: initial position, initial velocity, final velocity, acceleration time. Okay, so initial position, let's start there. Well, we're still down here, aren't we? We're still at the origin. All right, and so x naught is equal to 0, y naught equals 0. That is still correct. Okay, but now the final position is not at the top there. It's at the top of the hill. And so this is now incorrect. Okay, what should you get? Well, x, how far did you move horizontally before you landed? We don't know that. That's still unknown. So that much didn't change. Okay, but the y we do know now. See, before we didn't know it, and in fact we wanted to solve for it because we didn't know the maximum height. Okay, but now we do know this height here, and let's see if I can draw it. Okay, I'm kind of getting it. I might remove that line in a minute. But you see, I just take that point there and I get the y projection off of it. And we know that the hill is 20 meters high. And so if we get the y projection of the ball just before it hits the top of the hill, that's 20 meters. Okay, so let me get rid of that. Otherwise, I'm going to make a mess of my diagram. So that's 20 meters. Okay, in other words, that point there, that purple point, has coordinates x equals, I don't know, y equals 20 meters. Okay, so you see how that changed. And if you just blindly use the numbers from part A and B into part C without saying, I need to rethink these, that's another place where an error can be made. Okay, so if you move the initial position around, well, then you have to rethink the initial values. If you move the final position around, then you got to rethink the final values, and so on. Okay, and so there's the new final position. The initial velocity, that did not change because nothing changed about the initial situation. We're still starting at the origin, we're still starting with the same velocity, and so on. And so that's still true. And I mean, those are just the equations, because even the numbers that you put into those equations are new. But now when we get to the final velocity, it's different. Okay, your v naught x, so your vx is still the same because it doesn't change anywhere along the motion, but the vy is different. Up here, vy was 0 because you had reached maximum height. But I think you can see that since you're coming down, just before you hit the top of the hill, you're heading downwards there. Okay, your vy is not going to be 0. Okay, and this is kind of something that's a bit subtle here. Okay, vy is equal to unknown, definitely not 0. In fact, you can even say that it's negative. You can say that because it's coming down. Okay, but don't say it's 0. Because you might think, oh, it's 0 because it hits the top of the hill. But no, the equations don't know anything about the hill. Okay, and so as soon as the ball actually starts to interact with the top of the hill, then what's going on is the there's other accelerations besides the acceleration due to gravity, and the equations don't work. So you really don't know Vy there. Okay, let me switch to the text editor and we can finish this problem off. And so for this one, actually for C, D, and E, how long until it lands on the top of the hill, we've got a new final position. We have to rethink all of the values again. And so we get these values. Some of them are the same, okay, but some of them are not. So I say here, reanalyze, because the final position velocity has changed. The initial is still the same. So the initial position is still the same here, like that. And the initial velocity is still the same. But the final position is, as I said, it's the x is unknown, but y is 20. Okay. And the final velocity, that's also changed. Yeah, the vx is still the same, but the vy isn't. Okay, before we had vy is equal to 0. And the reason we had vy equals 0 there was because we had reached maximum height. But here, we're no longer at maximum height. We're heading downwards. And so there is a negative value to Vy. All right. And again, don't think of it as after it hit. As soon as that ball starts to interact with the hill, like it's going to be a complicated interaction. It's going to hit it and maybe bounce a few times. There's nothing in these equations about bouncing, stopping, or anything like that. As far as the equations are concerned, those 4 equations, you have an infinite parabola on both sides. Okay, and so the better way to think about these problems, whenever you're going to have something landing or hitting or anything like that, think about it as just before hitting. Okay, and I think you would agree that just before the ball hits the ground, it's moving. It's got a velocity. It hasn't stopped, and it's got a downwards velocity. I mean, it's got some velocity to the x, but it's also got some downwards velocity too. Okay, so there it is, and then you say, okay, great. Now that you have that, the next step is look at the equations and solve them. And for this one, we want time again. Okay, so I'm going to cut and paste the whole solution here because why not? All right, and we'll go through it slowly. All right, so let's reread the question. How long before it lands on the top of the hill? What do we want? We want time. Okay, and if you go through those 4 equations, you're going to find that the only one that'll work, that'll give it to you, will be number 1. Okay, number 3 you can't use here. I can go back to them for a sec. Okay, number 3 is out because it doesn't give you time, and you want to solve for time. Number 4 doesn't work because it's purely horizontal information, and that's not enough. Okay, you don't know the time, you don't know x. That's another way to think about it. Okay, number 2 we also can't use. You don't know the time, and you don't know Vy. Okay, don't say it's 0. All right, because it isn't. All right, and so number 1 is the only one by process of elimination. All right, so use number 1, and when you do that, there it is, just repeated. Okay, I substituted in the numbers. That's pretty easy. I mean, y is 20, ay is negative 10, v naught y we found was 21.7, and y naught is 0. Okay, so then I just simplified that. I multiplied a half times negative 10 is negative 5, subtracted 20 from both sides, and it simplifies to this. Okay, and you've got a quadratic. There's no way around that. All right. So I've always done this, even it's like I guess since I first learned it in high school. I mean, you don't have to do this, but I like to find dividing through by the coefficient a. And so when you do that, that's the coefficient a right here is negative 5. So you divide negative 5 by negative 5, that gives you 1. And then 21 positive 21.7 divided by negative 5 is negative 4.34, and negative 20 divided by negative 5 is positive 4. The reason I like doing that is just so it sets that capital A coefficient to 1. Okay, I'm sure you guys have solved the quadratic lots of times, so hopefully I'm not going too fast over this, but there it is, with the coefficient A factored out. And that means that A is equal to 1, B is equal to negative 4.34, and C is equal to 4. Okay, the quadratic equation formula, T is equal to minus B plus or minus, because there's always two roots, the square root of B squared minus 4AC divided by 2A. Remember, capital A is 1. Okay, so substituting in the numbers, that's minus B. Watch it, it's minus, even though B is negative, there's another minus in front, so it's minus 4.34. Okay, plus or minus the square root of b squared. When you square b, if it's a negative number, it's going to give you a positive because you're squaring everything, including the negative. So that negative 4.34 squared, make sure it gives you a positive number. Depending on how calculators work, sometimes you'll press the negative and you'll press the 4.34 and then the square button. And it might square just the 4.34 and not the negative part. Just remember, when you square a negative number, you get a positive number because the negative times the negative is positive. Minus 4ac, that's 4 minus 4 times 4, all divided by 2. And that works out to two roots, 3.01 and 1.33. Since all our work is open book, all of the tests are open book and everything like that, this should be pretty easy. I mean, a lot of programmable calculators have the quadratic formula already in them. Okay, if not, there's this site right here, and it's math.com. Math.com has a lot of good formulas there, kind of high school level formulas and trig level formulas. So, it's a really good site. And there's the one for the quadratic. Now, you may not remember that URL there, but, if you just go to Google and you Google for solve quadratic equation online, you're not only going to get this site, you're going to get a whole bunch of them. And then all you do is you just put the coefficients in there, press a button, and boom, out comes the answer. Okay, so there's nothing wrong with using a calculator to solve things for you, but I mean, once you understand the quadratic and you've done it a dozen times, it kind of becomes annoying and just tedious to do it again, because you're not, it's not that you don't understand it. You understand it, it's just you might make a mistake. But there it is. I just mentioned that in passing. Okay, you get 2 times, and here's the thing. You say, well, which of the 2 times do I want? And here I just say, well, using the diagram, you want the 3.04, not the 1.33. So let's go back to the diagram and take a look at what that 1.33 means, because there's 2. Now, oftentimes you'll get a positive and a negative number, and people will go, well, obviously I want the positive time because it's after t equals 0. It's after I started the stopwatch. But here you get 2 positive times. You're wondering, what do those 2 positive times mean? Well, let's go back to the diagram and see. Okay, so let me draw here in purple. Let me draw in purple like that. That line right there, like that. Okay, what is that? That's the 20-meter height. Okay, that's 20 meters high. When we substituted into equation number 1, what we were effectively asking was, what are the 2 times, or at what times is the ball going to be at the 20-meter height? And so follow the black trajectory here. Okay, I know the diagram's getting messy, but follow the black trajectory, and you'll notice that it crosses the 20-meter height, the 20-meter point, once on the way up, and of course, once again on the way down, which is the top of the hill. Well, on the way up, guess what that time is? That time corresponds to the 1.33 seconds. Okay. And this one corresponds to the 3.01 seconds, okay? And so it's pretty obvious that since you want when is the ball going to hit the top of the hill, you want the 3.01 seconds, okay? So that's the answer. But I want to show you another symmetry here because we also found the time for the maximum height, that was 2.17, right? And the parabola is symmetrical. And so the time it takes to go from that 1.33, that is when you pass the 20-meter mark on the way up, let me fill that in here like that, the time it takes to travel up there like that is exactly equal to the time it takes to go from maximum height back down to the 20. So from 20 to the maximum height is a certain amount of time. It's the same amount of time from the maximum height back down. It actually turns out to be 0.84. I'll show you how I got that number in a minute. In other words, when you pass the 20-meter mark on the way up, you go from that time until you get the maximum height, that's 0.84 seconds. And then from maximum height back down to the 20-meter mark is another 0.84 seconds, okay? And so the two solutions here are exactly symmetrical around the maximum height, okay? And well, that kind of makes intuitive sense. Let me go back to this, and you can see what happened here. So, maximum height was 2.17. That's the middle of the parabola, the so-called vortex of the parabola. Well, if you take 3.01, you can write that as 2.17 plus 0.84, okay? And the 1.33, you can write that as 2.17 minus 0.84. Okay, just pointing out a symmetry of the parabola. Okay, did we answer the question? I mean, I was all over the place. And so let's make sure we answered it. How long before it lands in the top of the hill? The answer is 3.01 seconds. Okay, let me look in the chat. There were a lot of steps there. Okay, let me actually type everyone okay. All right. Well, let's answer the next two questions. They're pretty. It's pretty straightforward after here. How far did it travel horizontally before landing? So what is that? Horizontal is x information. In other words, I want to find how far it went horizontally. And back to our equations here. There's only one that has horizontal information. It's number 4. Okay, so we want to use number 4. And let me just cut and paste that answer. All right, so substitute into number 4 to find x. And there's the equation. All right, and we found that v naught x was 12.5. Here we want the time until it starts to land, and we find that, and of course x naught is 0. Okay, it starts at the origin, and so we find that it travels 37.6 meters horizontally. Okay, that was easy enough. And finally, I ask, what's the velocity? And here I was very clear, just before it hits the top of the hill. Okay, so Vy is not 0. And, when you do that, you're going to get a Vx and a Vy. And so I asked for just the magnitude. Okay, now the reason I did that is because as soon as you hear magnitude and direction, you're talking polar. What are the equations going to give you? They're going to give you Cartesian. So for your final velocity, you're going to have a Vx and a Vy, but that's not what I'm asking for. I don't want the Vx, I don't want the Vy, I want the magnitude. And how do you obtain the magnitude from Vx and Vy? It's Pythagorean theorem. Okay, so let me cut and paste the formulas, and then I'll explain that. All right, so there we go. All right, so we're talking about final velocity. Whoops, let's clip there like that. Okay. We want the final velocity, so we want Vx and Vy. All right. We already know Vx because, as I said, Vx doesn't change. No acceleration in the x direction. If it starts off with an x component of the velocity of 12.5 meters per second, it continues. Okay. And for Vy, actually I said use equation 3, but we could use 1 or 3. Okay. No, actually, you could use 2 or 3. I'm sorry. You could use either 2 or 3. I decided to use number 3 because it actually shows that you've got two solutions there. And so number 3 is Vy squared is equal to V naught y squared plus 2ay y minus y naught. Substituting in the numbers and solving, we get to this point here. and that's Vy squared is equal to 70.89. Okay, and here we have to be careful. Okay, and here's why. Even that is a quadratic because there's a square. When you take the square root of that number on your calculator doesn't know that there are two roots. When you take the square root of that, it's just going to give you positive 8.42. But be careful because there's both a positive and a negative value, okay? And in fact, in this case, we want the negative value. Why? Because Vy is going down, okay? You might say, what's the positive value? That's the Vy when it passes the 20-meter mark on the way up. On the way up, it's going to be traveling with a Vy of 8.42, positive 8.42. On the way down, when it's about to hit the top of the hill, it's traveling with negative or downwards 8.42 meters per second. Okay. At this point, we have both Vx and Vy, but that's not what I want. I want the magnitude. And you say, well, how do I get the magnitude out of this? And as I said, you use Pythagorean theorem. This is I've been saying Pythagorean theorem, but this is basically, you know, the conversion from Cartesian to polar. So we have that Vx is equal to 12.5 and Vy is a negative 8.42, but we want the magnitude, and the magnitude is basically that polar r value that you saw in my lectures on vectors. Okay, and so here the magnitude v is equal to the square root of the two components squared. Okay, so you do Vx squared plus Vy squared, then take the square root of that, and that gives you the component. And it's easy enough, but just be careful. Once again, it's like the negative gets squared along with everything else, so it's negative 8.42 all squared. So that had better be a positive number. You know, in this case, you'd actually get a value, but like sometimes you'll get a negative under the square root this way. Yeah, just be careful. You know that it's the whole number squared, including the negative sign in front, and that gives me a magnitude of velocity of 15.1 meters per second. Okay, so let's see, what time is it? We're running out of time, but I can quickly get the last bit of it done. So let me see here. Any questions in the? Can you explain me non-constant forces? Oh yeah, yeah. This is actually a private chat here, Rajaswari. So I'm sorry about that. I can't. All right. So let me just give you the last two problems to work on, and then I'll do the fourth one very quickly. So repeat this on your own as part of the practice. Like, you repeat it. By repeating it, I don't mean like just copying it from one. Like, just look at the problems and solve them on your own without looking back at the solution. And if you have to, look back at my solution. Okay. But then once you've done that, repeat the entire problem again. But this time, assume that you're purely on ground level. So the one I did was you're at ground level and you land on something higher. For the first practice problem you're going to do, you're at just ground level. Okay, and so the ball leaves ground level and lands at ground level. And then for part 3 here, practice problem number 3, again, do this on your own. You're going to be at the top of a hill, 20 meters high, and you throw the ball up, and then it lands at ground level. Okay, and in that case, you're going to have all possibilities where you're throwing it from below where it lands, at the same level of where it lands, or you throw it from higher than where it lands. Okay, and you've got all three possibilities. All right, and I won't check these, but if you have questions, you can always ask me afterwards, like during our office hours. And on the test, you know, there's going to be one variation of one of these three possibilities, so they're worth working through carefully. Let me quickly do this one. I'm riding a bicycle around a corner of radius 7 meters. How fast can I turn without slipping? If the fastest I can turn without slipping is where my acceleration is 1/4 of the acceleration due to gravity. How fast can I go around the corner? Okay, so these problems, these uniform circular motion problems, they really are quite straightforward. There's just 3 equations here. Let me cut and paste the let me cut and paste the numbers there. You don't really need a diagram for these. You don't really need a diagram. You have that the radius is 7 meters. I tell you that. Okay. You have that the acceleration, that's the acceleration keeping me on the turn, is 1/4, 0.25 of the acceleration due to gravity 10. In other words, 2.5 meters per second squared. So I just gave you that in a fancy way of saying what the acceleration is. But it's kind of nice to know. You say, well, yeah, I can turn, but I can't turn with more than a quarter of my weight, something like that, okay, or 1/4 of the acceleration due to gravity. So I give you r and I give you a, and I expect you to find v, how fast. Whenever you ask how fast, that's v. I say, well, how fast can you go around the corner? You want to solve for v. There are the three equations that you have, okay? Capital T is the period. If that's the time it takes to make one complete revolution around a circle, okay? One complete revolution around a circle. All right, so the first one is v is equal to 2 pi r over t. And it does give you v, and you do have r, but you don't. I didn't give you any time information, so you don't have the period. You can't use that one. Number 2 is the same, but it's a in terms of r and t. Okay, and so you can't use that one, and you don't want that one either because you're trying to solve for v. So number 2 is out, and so obviously number 3 is the one you want to use. A is equal to v squared. A is equal to v squared divided by r. Okay, now you're solving for v, so I like rearranging it before I plug in numbers, okay? And so, just take that equation number 3, multiply both sides by r, okay? And then take the square root of both sides. And here we don't have to worry about the negative solution because we're just talking about the magnitude of v, like how big v is, not any direction. The directions were in that diagram I gave in the pre-recorded lecture. It shows the centripetal towards the center, centripetal acceleration towards the center, and the velocity tangential to the outside of the circle. Okay, so in plugging in the numbers, you get 4.18 meters per second. Okay, and that's the answer. Okay, I did translate that into numbers that are more intuitive, and the only reason I did that was just to help your intuition. 4.18 meters per second, that's roughly 15 kilometers per hour, or about 10 miles an hour, and that kind of makes sense. If you're going around a corner, which is about 21 feet in radius, okay, and you want to do it safely, about 10 miles an hour is about right. I mean, you probably could do it faster, but if you want to do it safely, 10 miles per hour sounds about right, or 50 kilometers per hour. Okay, well, there it is. There's the tutorial, and let me look at uh, the live stream here, and I'm not seeing any questions from you guys, so um, if this is fine, we can just call it a class. Okay, is everyone okay? Can I end the live stream? All right. If there are no questions, if I don't see any questions in a few minutes, I'll just end the live stream. Everyone all right? Shall I end the live stream? All right. Good. If you have questions later, that's what the Google Hangouts are all about. All right. Okay. Ending the live stream.